Okay, one announcement before the class. I updated our class page. Two stuff. The first one is a reading assignment. I'm asking you to read this document, chapter 30 in Zinc 7000 TRM, Technical Reference Manual. It is analog to digital converter, okay, ADC, okay, analog to digital converter. So it is essentially taking analog input. Okay, if I explain briefly, ADC, right? It is taking some analog input and give you digital output. Okay, so very simple. The function itself is very simple. So if you click on this, so it says ADC 12-bit and 1 mega sample per second, meaning that 12-bit, it is 12-bit data. Okay, and then it is sampling 1 million data point, million sample per second, right? Per second. Every second it is taking 1 million samples, assuming that time, right, and voltage. So it is changing like this, right? Then this ADC is taking first sample second and 1 million samples every second and give you 12-bit output. So we are going to play with that 12-bit output. Okay? So in our application, we are going to connect light sensor. Okay, here. Then ADC will give you some information about that, and we are going to check out the data in light sensor. Okay, so the first one, ADC. Okay, please read this one. Second one is a little bit serious. Okay, presentation. I'm asking you to cook up PowerPoint. Okay, so what is this about? This is about motion sensor, accelerometer, motion sensor or accelerometer. Okay, so read this specification and then prepare PowerPoint. Okay, and I'm going to ask some of you to present in this class. Okay, so, and the due is not fixed yet. So later this week or early next week, I'm going to fix the date. Okay, so you have some time. To read and cook a PowerPoint. And if you want to know, if you are confused, then probably you want to check out this Arduino lecture. So I gave this lecture, okay, of using this motion sensor before. So probably you want to check out this my lecture, okay, YouTube lecture, okay, this one. So essentially that is the one this is the one. This is the one, motion sensor, this one. Here. So the small device at the center, of this board, this one, this square, right? Very small square device. That is motion sensor. Okay. So we are going to take some information from this connection, and play with it. Okay. So before that, you need to understand what is the function of this motion sensor, right? What kind of capability it is providing. Okay. So you read this data sheet and prepare PowerPoint. Any question about this? Okay, let's move on. to instruction discussion. Today we will finish up this instruction discussion. Then we will move on to handling I/O devices. Okay, I/O devices like sensors, from simple I/O devices, right? GPIO, UART, timer to sensors. Okay, so last time I think we were here, swap instructions. Okay. Okay, this one, Guyun, can you please read this one more time?
Swap instruction, SWP swaps the contents of memory with the contents of a register. In this special case of a load store instruction, it performs a swap atomically, meaning that it does not release the bus until it is done with the read and the write. It is useful to implement semaphores and mutual exclusion mutex in an OS.
Okay, thanks. Swap instruction, that instruction is provided to implement, this is important, the mutual exclusion in operating system. So what is mutual exclusion, right? Mutually exclusive, only one guy can use shared resource. The best example is printer. Last time I gave you, right, the printer. So think about, two guys are sharing one printer. And then, before you sending your printing job to the printer, system should make sure no one is using that printer for now, right? If the printer is being used, then you have to wait. You have to wait until the other guy finishes its printing job, right? One shared resource, right? So to use that shared resource, you have to make sure, right, that is not being used by other guys, right? Other guy, right? And that is typically implemented with a lock variable in memory, right? Lock. So last time, I'm trying to give you, multi-processor system example, but we don't have to go that far. Single processor system. Think about a single processor computer system. You have only one CPU, then memory, and we have a lock variable. This one, this lock. Let's say this variable. Zero. Zero means printer is free. One means it is occupied or locked. Right? Someone is using. Someone is using. It is being used. Okay. Someone is using that printer. Okay. So it is initially initialized to 0. So no one is using printer. Okay. And in computer system, operating system is managing many different tasks, many different processes or tasks in a time multiplexed manner, right? So one CPU based system, then time, right? Assume that you have 4 different tasks. First one is hello world, right? Hello world. And second, MP3 player. Okay. Then Chrome. You want to surf the web. Okay. Then the last one, what do you want? MS Word. Okay. Then you want to run these 4 different tasks, 4 different processes, okay, simultaneously. Okay. Then what do you have to do? Operating system is managing these 4 different tasks in time multiplexed manner. So for example, every 1 millisecond. So every 1 millisecond, OS is doing context switch, okay, to kick out this guy. Okay, you go out. I need to run MP3 player. So 1 millisecond elapsed, then operating system, okay, you are done. Okay, I need to execute this Chrome. Okay, next 1 millisecond, then MS Word and so on. Okay, so that is time multiplexed management of tasks. Okay, so every 1 millisecond. The thing is, let's assume this first task is your HWP. Okay, your HWP, and second task is other guys. HWP, your friend. You and your friend. Okay, and you want to send the printing job. So you need to check out this lock variable. So let me write the pseudocode without that instruction. How would you check this lock variable and update this one to one? So probably you want to use LDR instruction. LDR. Okay. So read from this memory location. Okay, and store into R0 register. Okay. This location, log location. Okay. Read that data. If R0 is equal to 0, R0 no one is using the this variable, this printer, then you want to store let me pseudocode, right? 1 to this location. Okay, otherwise then you have to keep checking, keep branch loop. Okay, probably better code. Okay, so this one if R0 is equal to 0. So probably you can use a CMP instruction here, right? In assembly, CMP compare, right? R0, then constant 0. That is going to update NGCV. Okay, so that instruction, STR not equal, right? NE not equal. These two are not equal, then you update. Okay, 1 lock. And B not equal, then you have to go back. Not equal, 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 sorry, equal, I got confused. Equal, right? These two are equal, right? Equal, then you update that to 1. Okay, equal, then you have to go back. Okay, you have to go back. So probably that is better code, right? Correct, right? R0 is equal to 0. That means no one is using that printer, right? So equal 0. Okay, 0, then update. Then I'm confused. Okay, so not equal here. So how about that? Equal, then update. Not equal, then you have to go back. Is it correct? Equal, right? Equal, then do store operation. That store operation. Okay, and not equal, then you have to keep checking. Okay, not equal, you have to keep checking that log variable. Yeah, so it doesn't. Okay, so I think that's correct. So then what is the problem? Okay, so if you use those instructions to implement that checking mechanism, lock variable checking mechanism, we have some problem. So what do you think? What is the problem? What if CPU executed that instruction? Assume that initially this one is 0. Initially this one is 0. Then you executed this LDR instruction. Okay. Then operating system decided to kick out this checking your task. Okay. Then here. Okay. Context switched out. You got context switched out. Then new task. Okay, your friend's task. Kicks in, got executed. Then that guy is doing the same operation, same thing. Okay, this guy need to send the printing job to the printer. So it is, executing the same piece of code. Then it is reading. This code is reading lock variable, and found out no one is using that printer. So it is that guy is trying to update this one to 1. Okay. Then at the end of the 1 millisecond, then operating system decided to run that task again. Okay, this 1 and 2 and 1. Okay, your task, you. Then you keep executing. Okay, keep executing from this line. So R0 contains 0. Then you think, okay, no one is using that printer. So what happens? Two guys are sending printing job at the same time. Okay? So we have some problem, right? So with one instruction, that mutual exclusion cannot be guaranteed. This mutual exclusion. That is why CPU is providing some special instruction, okay, to support this mutual exclusion. Swap is very intuitive instruction. Okay, it is atomic. Okay, look at this swap R0, R1, then R2. R2 is a lock variable, right? Lock. Okay, so from here you want to read. So you want to read, okay, and place into R0 register, and this one initially that R1 register contains 1. So it is updating this memory location. This is read. Here LDR operation is LDR. Okay, and this one is store operation, STR. That store operation. And it is atomic. You cannot separate these two operations. It is atomic. Okay? It is not breakable by hardware. It is guaranteed. Okay, so you are reading. So what does that mean? 0, initially 0. Then you are reading from this memory location. So R0 will contain 0. This guy is 0. Then 1 will be updated. 1 will be updated. Okay, what if this guy is 1? What if this guy is already 1? Okay, the printer is being used by other guy. Then reading, okay, reading. So this one is 1. And you are updating 1 to 1. So no change, right? 1 to 1. 1 to 1, same value. Okay. So in that way, mutual exclusion is guaranteed. Okay. Same thing goes to multiprocessor system. Okay, you have two CPUs. Okay. Multiprocessor system, 2 CPUs. And main memory is shared by these two CPUs. Okay. And assuming that you are executing the same piece of code, this same piece of code here and here, okay, to check this lock variable. Okay, and the problem is, this bus, this connection is shared by these two guys. Okay, only one guy can use this connection at certain time. Okay, these two guys cannot send a request, cannot access main memory at the same time because the same connection, right? So one at a time. So assuming that there is an arbiter, okay? So we have hardware component called arbiter. This guy is arbitrating this bus access. So there should be some connection from CPU to here, request. Okay, I want to access the bus to access memory. I want to use the bus to access memory. That is a request. Okay, and response, this guy is sending grant. This physical connection, right? Physical connection. If two CPUs are requesting memory access at the same time, there is some arbitration mechanism, right? Random or priority based. Okay, you have higher priority. Then if two guys are sending requesting memory access, I'll give you permission. Okay, so depending on the mechanism, right, you implement in hardware, right? So only one guy can access. So in this case, assuming that CPU is executing this code, CPU1 is executing same piece of code, then this guy, it is initially 0. Okay, the first instruction, this guy is reading 0, right? Reading 0. Then arbiter decided to give permission to this guy. Okay, so before CPU 0, before CPU 0 updating this location 1, okay, that guy have the permission to access this location. Okay, so then you end up reading same data, not this updated data, because at this time the CPU 0 stopped at this point. Okay, here. Okay, so probably here. Okay, so it is about to execute this guy. It is about to execute store instruction. Because arbiter didn't give a permission to CPU 0. Okay, so second CPU, accessing this memory location. Then these two guys think, okay, no one is using printer, so 0 and 0. So trying to update, okay, 1, and this guy also 1. So you have some conflict. So mutual exclusion is not guaranteed. Okay, but if you use a swap instruction, it is not breakable. It is atomic operation. Okay, so until you finish, until CPU 0 swap, CPU 0 is executing swap instruction until CPU 0 finishes executing this swap instruction. The bus is not released. This bus, the arbiter does not release the bus. So this is a read operation, write operation. Okay, read operation, write operation. It is not breakable. Okay, atomic operation, atomic. So for that purpose, there is a bus signal called the lock in ARM XC. We are talking about ARM CPU, right? ARM CPU. Okay. So if we talk a little bit more detail about that mechanism, if you think about this bus connection, this shared bus connection, there are bunch of wires. The first one is obviously address connection, okay, and data connection, okay, and control signal, not bidirectional, control signal, control. So control signal, using this control signal, you can deliver that information. What information? It is not breakable. Okay? Control signal. So multi, bit control signal. So that is a protocol. Okay, protocol, hardware design protocol. Okay. Does it make sense? So go through this example, right? So simple. Reading, so before state and after state. So look at this R2. R2 has 9,000. So at 9,000 location, you have this data. Okay, R1 has this one, 4 ones and 4 ones and 4 twos. Okay, so after executing this code, what do you expect? So that data, the data will be loaded into R0 register. This R0, okay, read, and memory will be updated with R1. Okay, so 1 1 1 1 2 2 2 2. So after status. Okay, so first read 1 2 3 4. That goes to here. Okay. It is very important mechanism. Think about, mutual exclusion. Not only this Windows or Linux, real-time operating system that is used in embedded system, right? Even in real-time operating system, there are many tasks you want to execute. Okay, then these many front tasks want to access shared resources. Then mutual exclusion should be provided. That is critical section. Okay, critical section. Printer is critical section. Some shared data structure. That is also critical section. So that is semaphore example. Okay. So log or semaphore, right? So you are reading. So memory location. So trying to analyze this one. Okay, R1, right? R1. Memory location. Think of it as log variable. Okay, log variable location. And then R2. R2 is initialized to 1. So this R2. Okay. So R1. So you want to read from this location. Okay, log location or semaphore location. And store into R3 register. And then R2, 1 is going to be updated. Okay. The next instruction is reading, checking the data you just read from memory. Okay. So that is equal to 1, BEQ equal to 1. Then that means what? That is equal to 1. That means someone is using the shared resource printer. So you have to go back, keep checking the memory location until the other guy release that shared resource. Okay. So acquire the lock acquire and release. Try to acquire the lock, right? And release. You're done. And this one is very intuitive to understand why you need mutual exclusion, why you need and how to guarantee mutual exclusion with swap instruction. But that is a deprecated instruction. Okay, you cannot use in Cortex A9 deprecated. Okay, instead you have to use these two instructions: LDR exclusive, load exclusive, and store exclusive. Those two instructions. I'm not going to talk in detail about this. Okay. So two separate instructions. Separate instructions. Okay. So check out this, because we are not going to talk. We are not going to use those instructions in this class. Okay. So we are not going to talk about this. Okay, that is about ARM version 7 instructions, and then this software interrupt instructions. Okay, and CPSR related instructions. We will talk about that next time. Not next time. After probably a midterm exam. Okay, this SVC, software interrupt instructions, and CPSR manipulation instruction. This one, CPSR register. You can read from CPSR. You can update CPSR registers, CPSR register, okay, with that instructions. Okay, that is about instructions. Any question before maybe move on to next topic? Okay, we want to now play with now IO devices. If you think about the lecture I gave so far, we assume we have only two components, right? CPU, ARM CPU, and memory, right? And your program, right? Your code is loaded in memory, and CPU is reading your instruction one by one and execute it. That is our computer model, right? You have only CPU and memory. And if you have a CPU and memory in computer, it is not that useful, right? There is no interface. There is no interface for human control, right? You cannot control this device. You cannot see anything, right? Reading instruction and executing some code, it is not visible to you, right? So we need some component to control our computer, okay? And to see something, right? So those are IO devices, right? So keyboard, right? Mouse, GPIO, right? GPIO, UART, timer, USB, you name it, right? So except CPU and memory, all other devices are IOs, right? So we want to control these IO devices, right? That is complete computer system. Okay? So before we play with these IO devices, you need to understand very important concept called memory map. Okay? So now you want to read, right? So like you read data from memory, some data 1 and 2. Okay, so all IO devices are providing registers. Okay, many different registers. Okay, so using assembly code, you want to read. Okay, and sometimes update these registers. The question is how to read from this register, how to update. What instruction do you have to use? Okay, so let's talk about this. That is computer system. Okay, so we have CPU, memory, and green boxes, IO devices. Okay, this one, P1, can you please?
Pentium 3 is a 32-bit machine with 36-bit physical address. A means that address bus has 36 pins for address. Note that we count from 0 in hardware. D means that data bus has 64 pins for data. What is the max address A can address? 64 gigabit minus 1. So it creates 64 gigabyte space, meaning you can theoretically have up to 64 gigabyte main memory installed in your PC.
Okay, let's continue to read and I'll explain. I don't know. Jisung, can you please?
Computer only knows two kinds of devices, memory and I/O devices. For example, main memory and BIOS ROM in your PC are memory devices. Keyboard and mouse are I/O devices. When building a computer system, the address spaces for memory and I/O devices are typically assigned in advance by hardware. Then, how does CPU access these devices? Very simple. To access memory, CPU generates memory transactions. To access I/O device, CPU generates memory transaction if the I/O device is memory mapped. CPU generates I/O transaction if the I/O device is I/O mapped.
Okay. Thanks. You know, in computer, there could be two different spaces: memory space and I/O space. Okay, memory space and I/O space. There could be, okay, but in some computer system there is only memory space. Okay, so in x86, you have two different space: memory space and I/O space. But in ARM, we have only memory space. There is no I/O space. So CPU vendor is making the decision. Do we have to provide two different spaces or just one is enough? Okay. And RISC-V also, RISC-V is providing only memory space. Okay. There is no I/O space. Okay. But even in x86, I/O space is not that frequently used. Okay, so the reason why x86 is providing I/O space is because to support legacy software. So software developed in 1980s, 1990s, those software may access those I/O space, okay, for execution. So you don't want to break that legacy code. That is why Intel is still providing very small I/O space. Okay, these days, you know, you can say x86 x86 also is providing, you know, memory space only because that space is for legacy, you know, software. So then what do you mean by this space? The space is created by what? CPU is providing address, right? And there is a data connection. Let's say you have 32-bit address, CPU, right? So we are talking about 32-bit ARM CPU, right? Everything is based on 32-bit, right? Register file, each register, 32-bit, data path, 32-bit, right? 32-bit, and program counter is also 32-bit. That is actually program counter is connected. That, you know, address. Also, that is for instruction fetch. And for data access, think about this LDL instruction. R0, R1, then probably 4. So R1 plus 4. That is memory location you want to access from, right? R1 plus 4. So probably if ALU is doing that, you know, addition, that ALU output should be somehow connected to this address bus. Anyway, it is, you know, 32-bit, typically 32-bit, because program counter is 32-bit. You know, the address is 32-bit for data access, right? Then, if CPU is providing 32-bit address, then it is creating how big space? It is creating 2 to the power of 32 byte space. Space, right? Empty space. Space, space, right? There's nothing at the beginning, right? So it is creating this space. Okay. The size 2 to the power of 32. Okay. That is 4 gigabyte space. Okay, from to here too. So at the beginning, space means there's nothing, just empty. And when you design hardware, when you design embedded system, when you design a motherboard, okay, hardware system, you have to populate actual hardware component. You have to populate actual hardware component onto this space. For example, main memory, right? You have 4 gigabyte space, then probably, okay, I want to have main memory here. Here, actual main memory DIMM. Okay, DIMM, DRAM, SDRAM, right? 2 gigabyte. Okay, I want to map actual main memory in lower half, starting from 0. The last one, 8 Fs. Okay. So I want to map actual main memory here, and I want to map my GPIO device here, and timer here, and UART here, USB here. You want to populate, okay? You want to populate actual hardware component onto this space. That is called memory map, this one. This one is called memory map. Okay, so for now, let's talk about this only memory space. It is creating this memory space, okay? Memory space. And inside the space, when you design hardware system, think about that you are hardware designer. Okay, you want to make decision. What decision? Okay, main memory start from 0, and what is the last address? 2 gigabyte. Okay, then so half of this, right? So 8 0. So one below. So 7 Fs. So 0 to 7 Fs. So that is 2 gigabyte. And what is the memory range, the area? Okay, you want to map this UART IO device to. You make this decision and populate it, right? And you have to make connection to provide. You have to make physical connections to provide that memory map. Okay, so let me show you example. Better to show you example. So in this simple example, ARM CPU is providing, so generating 32-bit address, right? Address, this one, 31, 30, 21, 29 to 0, so 32-bit. And you want to create this mapping. That is the one you want to design. Again, you want to design, hardware system, not just using design, right? Actual hardware system. And that is the map you want to create, memory map you want to create. Okay. So in this, this is not realistic, but for explanation purpose, right? So main memory occupies 1 gigabyte. Okay. 1 gigabyte. UART is occupying 1 gigabyte, 1 gigabyte, 1 gigabyte each, right? Each device 1 gigabyte. Then this is the address. So 4 gigabyte space, right? 0 to the last address is this one, 1 gigabyte. UART start address 4. Okay, I highlighted with red, in red, right? And the last one is 7 Fs. Okay, so this one timer starts from 8 to B. GPIO C to F. You can do some math. Okay, and then so that is the address, right? We want to memory map we want to create. Again, memory start from 0 to 3, UART 4 to 7, and so on. Okay, so 1 gigabyte each. And this one is binary representation of the first hexadecimal number. Okay, so 0, 4 zeros, 3, this number, 4. The point is, if you want to create this one, then that is differentiated by looking at 2 ms most significant bit. If CPU generate address starting with 00, that means CPU want to access main memory. Okay, CPU is generating address with 01, then CPU want to access UART, 10 timer 11 GPIO. Okay, so by looking at most significant 2-bit, you can tell. Okay, so CPU want to access which device. Okay, so we can use, so to create memory map, we can use this hardware component called decoder. This decoder. So what is the function? The truth table, this one. So this one is 2 to 4 decoder, right? You are taking 2-bit input, and decoder is asserting only one output. Okay, 0, 0, then Y1 is asserted. Okay, truth table, right? Remember in logic design, this is the logic design course. 0, 1, then Y1 is asserted, and so on. Okay, only one output will be asserted based on this input. Okay, so you can make that connection. Taking 2-bit input to most significant bit from CPU, then only one guy is asserted that is connected to chip select. It is very special connection. So every IO device and memory also. Memory and IO devices are providing special input called chip select. You are selected, right? Chip select. Here, this one. Chip select. That means, it is input is 1. That means, okay, you are selected. Okay, you have to prepare. Okay, because I'm going to access you. Okay, for example, decoder is asserting Y3. CPU generated that address, some address within this range. Okay, then GPIO is selected. Okay, then GPIO is responding to CPU's request. So using this decoder, you are creating this memory map. Does it make sense? Any question about this? So I'm trying to explain hardware system, how to cook up hardware system of your own. Okay, you want to use ARM CPU, then you want to have some IO devices. Memory is always there, right? And you want to have some IO devices, okay, depending on your application needs. Okay, then when you design hardware, you have to cook up this memory map, right? Memory map. How to create using decoder. Okay. So let me show you our hardware system. So we we have been using that hardware system. What hardware system? What is there? 7.2. So let me open Vivado. Where is that? Okay. Plus experiment. I think this is the one. Version 21. In the first assignment, you set up that environment, right? You installed Vivado, Vitis, and then you saw this hardware system block diagram, right? So we have here ARM CPU, right? This one, Jinc 7000. If you double click this, okay, you double click this, you have two ARM CPUs, right? Two ARM CPUs, and inside the Jinc 7000, you have many different I/O devices, I/O peripherals, SPI, I2C, CAN, UART, and so on. Many different I/O devices. Okay, so inside the PL, so that is PS, right? Light gray box. This one, processing system. Okay, little dark gray. This one PL, programmable logic. Okay, so inside the programmable logic, we added these two GPIO devices. Okay, so these two GPIO devices are providing registers, right? Some registers, I removed it, right? Some registers. We want to access those registers. How come? How to access? Check out this address map. Okay, address editor. So LED, two GPIO devices. Okay, this Vivado. Okay, this Vivado tool automatically assigned memory area to access registers inside LED or inside the switches. LED, okay, LED and switches. Look at this. LED, Vivado tool assigned this range 4120 to that address, 64K byte. Okay, and switches, and Vivado also assigned non-overlapping, right? If you compare that, it is not overlapping, right? 4121, right? Next location. From this to that location, 64K byte memory space for switch, right? GPIO. So we can use. So you have to use those addresses, those range to access registers in LED or switch. Okay. So if you double click this, then documentation about this GPIO. GPIO is the most simple IO device. Very simple, right? General purpose. General purpose input and output, right? GPIO, right? You can connect LED, you can connect switch, you can connect some actuator, anything you want. Very simple, super simple IO device. Download. Okay, it takes time. Okay, so let me close it. So you can check out this documentation to learn about that GPIO devices. To learn about GPIO, what does that mean? Learn about these GPIO devices. You need to figure out what kind of registers it is providing. That's it, right? And what is the function of those registers? Okay. 25. Okay. So in our example, you have GPIO, we have LEDs, right? So you can think it has only one register. Okay, that register is mapped at what is the location? 4120, right? 4120, 4120, 00. Okay, so that is called output register. Output register. Okay, and it is, I think, 8-bit register, and each bit is connected. Each bit is connected to LED. That LED. Okay, so if you program this register to 1, writing 1 to this bit in this register, then LED will be turned on. Okay, and then not just 1. Okay, you have LED, right? LED connected. Okay, so that LED, this is the one, LED. Right above this switch, you have 1, 2, 3, 4, 5, 6, 7, 8. 7 different LEDs. Oh, sorry, 8 different LEDs. So you can turn on or turn off those LEDs. Okay. By programming that register, just one register. Okay. Show you. So in the example code, let me show you. Okay. Let me do this. Okay. Here, this is sample code, right? Sample code. It is doing a copy operation from source to destination in this loop. And if you exit this loop, right, branch not equal loop, then it is doing what? Look at this. LED address. What is the LED address? 4120. 4120 and 4 zeros. Okay, the LED location. Okay, and then you are writing R1 is what? 5. 5 is what in binary? Binary 0101, right? Here you are writing 00000101, which is 5. Right? That means you want to turn on, I think, the rightmost LED and third LED. Okay, first one and third one. Okay, these two LEDs. So store operation, memory write operation. Okay, writing 5 to that location. So let me run it on the board. Okay, check out these registers. Okay. Then probably set breakpoint here. Double click this here, breakpoint, right? So I don't want to press F5 multiple times, set breakpoint and press run here, F8, F8. Then it will stop at their location. F8. Set breakpoint somewhere here, I think. Did I set breakpoint here? I don't know. Okay, F8. Okay, it stopped here. Okay, then let me press F5. Then what happened? F5. Oh, what happened? Okay, let me do it again. Something messed up. Let me do it again. I have to recompile probably. I didn't compile it. I changed the code and didn't compile it. Okay. Build. Yeah, I removed some code right here. Then didn't compile it. Okay, now debug. Okay, register and set breakpoint already here. Okay, so let me press F8. F8. Okay, stop here and F5. Okay, R0. R0 4120, right? GPIO LED register location. That register location. Okay, then F5, R1 is 5. Then last the instruction, store instruction, memory write instruction, writing this value to that register. Then these LEDs will be turned on. Okay, F5, these two, LEDs turned on. Okay, and then it is jumping to what? It is branching to CST main C code F5, then C code, right? Doing some garbage operation. Okay, F5, returning back. Okay. So what I'm trying to explain is this. We created this memory map. In memory space. Okay. And the thing is, these I/O devices, right? Main memory, right? It is too obvious. Main memory is mapped in memory space. So to access memory, you have to use memory access instructions, right? That is memory space. Inside this memory space, you populated actual memory. Actual memory, right? Memory. And we have GPIO, LED. Okay. To access data in main memory, you have to use to access data. Okay. Write and read. You have to use memory access instruction, right? STR, store instruction, and LDR instruction. Okay. So how about this GPIO? If this I/O device is mapped in memory space, it is called memory mapped I/O. Memory mapped I/O. Okay. To access registers in memory mapped I/O, you have to use same memory access instructions. Okay. To write STR, to read LDR, right? No difference if I/O device is memory mapped. Okay, that's what we are doing in Vivado project, right? So those I/O devices are memory mapped. Okay, memory mapped. That is why we use memory access instructions to touch registers. Okay, it's going back to here. Back to. The question is, how to create. I told you, right? There could be two different spaces: memory space and I/O space, and that is determined by CPU vendor. Okay, CPU vendor. Then the question is how to create two different spaces. Very simple. So you have address connection, right? This address connection. Okay, and that for memory space, I/O space, we can use the same address. Same address, this physical address. And to differentiate these two, we need just one bit output from a CPU, one connection output. Okay, let's call this mem or IO. Let's call this connection just a name, right? Name. And then for memory access, to access memory space, CPU should provide memory access instructions. Mem access instructions. Okay, memory access instructions. To access I/O space, CPU should provide different instructions. I/O access instructions. Okay, I/O access instructions. So in x86 case, x86 is providing move instruction to access memory space. And if CPU execute move instruction, that connection will be asserted to 1. It will be 1. Okay, if you execute memory access instruction. Okay, and that will be connected to chip select along with that address, right? Somehow that is connected to here chip select. Okay, and second, for I/O access, Intel x86 is providing in or out instruction. In instruction, out instruction, input, right? Input, reading from I/O device and writing. If CPU execute in or out instruction, that connection will be 0. Okay, this one will be 0. This mem IO. There is a convention. If you have bar here, then it is a low active. Okay. Okay. So 0 is active. IO access is active. So then how to make connection? Assume that you have keyboard here, mouse, some legacy interrupt controller, very old, 8259. Legacy interrupt controller. Then you have chip select, and you have to make connection, right? You have one output, and somehow you want to connect that guy to select, right? Like this. Okay, but you have to be careful. Okay, so one means CPU want to access memory space. 0 means CPU want to access I/O space. Then how to make connection? Simple. You need inverter here. What does that mean? Let's interpret. One CPU execute move instruction. Then one is connected, right? That is connected to here. Okay, that means chip select. That guy is selected. Memory, the hardware component in memory space, and inverter, right? So 0. So that those devices are not selected, deselected, not selected. So 0. Assume that CPU is executing in or out instruction. It is trying to access IO devices. 0, 0, then 0. Directly connected to that device. Chip select. So chip select is 0, then it is not selected. Okay, 0, then you go through this inverter, so 1. Then these guys are selected. Then depending on the address you generate, then one particular component will be accessed. So memory space, IO space. So if those IO devices are mapped in IO space, it is called IO mapped IO. IO space mapped IO device. IO space mapped IO space. There are two. IO device can be mapped in memory space, memory mapped IO, or IO space mapped IO. Okay, two different mapping. In general, you can ignore this. You can ignore this because it is not that used these days. Or virtually all IO devices are mapped in memory space. Okay, you don't have that connection. You don't provide, CPU does not provide separate instructions for IO access. Okay, so ARM is providing right? ARM is providing only memory access instructions. Using memory access instructions, you can access actual memory and also IO devices. Any question about this? So I'm trying to explain, so underlying mechanism to create memory map. Okay, in our class, you don't have to worry too much about that underlying mechanism, but because this Vivado, right? Vivado is automatically providing, this memory map for you. Okay, you add some IO device. For example, let me show you. You want to add one more GPIO. Okay, then it is suggesting, okay, I can make connection. Okay, you can make connection. Then, okay, new, what is that? This one, new connection, right? New device. So previous hardware system, we had LED and GPIO. Now we have one more. Okay. Then if you check out this address editor, look at this. System, Vivado, automatically assigned, look at this, 4122 to 64K byte. From this base to 64K byte. So the good news is when you design hardware system using Vivado, you don't have to worry too much about that. You don't have to worry about this memory map, but because you are graduate student, right? And if you don't know about this memory map, then something is missing, right? Something is missing to you. So I'm trying to bridge that gap, right? So how to create this memory map? By using decoder, using hardware component called the decoder, right? Okay, any question about today's class? Read this PowerPoint. We are done with this PowerPoint. So IO mapped IO, then memory mapped IO. Okay, so to differentiate memory space and IO space or memory map IO map, you need two things: instruction set support. Okay, and separate hardware signal from CPU, right? That signal, for example. Okay. So using that signal, you can physically connect these I/O devices, okay, with that address, decoder output. Right? So from next class, we are going to play with hardware component, I/O component. Okay, so from here, so simple I/O device. I already talked to you GPIO, but let me talk some more about GPIO. Then UART, GP timer. Then the one I ask you to read, right? Analog digital converter. Okay. Okay, that is for today. Anything you want to say? Okay, I'll see you the next time. Bye. Okay, thanks.